Okay, so today we will cover instant-based classifier. So this is another model that we can use to classify our data. This is called instant-based classifier because it is based on the instant that we are looking at. So based on the differences between two items. So the main idea is we want to measure the similarity between two examples or two instance or two samples using a specific distance measurement. And then we can decide whether these two instances are similar. So if they are almost similar or we find the nearest matching, then we can assign the label from a labeled instance to this unlabeled instance. Okay, so we can apply this, what we call it, nearest neighbor, because they are using distance method in order to assign the label to the new instance that we have. Okay, so nearest neighbor classifier are defined by their characteristic of classifying unlabeled. So unlabeled example is the new unseen instance that we have. And then what we can say in nearest neighbor is that we will assign the class of similar label example to this unseen label. Okay, so the classifier is very powerful and have been used for classifying or recognizing symbol, for example, in optical character recognition, facial recognition, or you want to predict whether a person will enjoy a movie or music recommendation. This is based on the previous watch list of the movie, or we can also use nearest neighbor to identify pattern in genetic data. So this is a very powerful classifier. Normally, if a concept is difficult to define, but you know it can be classified, then nearest neighbor might be one of the potential classifier that we can use. Okay, so in order for us to apply instant-based classifier, we need to know how does it work behind the scene. So we need to know how they compute the differences between two different instances in your database. Okay, so if the data is noisy, then you may have some difficulty, because in order for us to use the nearest neighbor, we need to have a clear distinction what feature can be used to differentiate the instance that we have. Okay. For the instant-based learning, we are looking at this key idea. Okay, so let's suppose we have all the training that we have, all the instant or all the example. So we have the individual item that we have, and also we have the label. So this is your instant, okay, this is your instant, and this is your label. Okay. So when we are looking at the nearest neighbor, when we are looking at the nearest neighbor or the most similar sample in our training data, then what happens is that we will find this nearest example and we take the label assigned to the new instance that we have. Okay, so this is the label of the most similar instance in your training dataset, and then I will take the label and assign it to the new instance that we have, because they are almost similar. So we can say that this could be belong to the same class. Okay. We could also have okay, this is only one. We could also have k. K nearest neighbor means we find k number of nearest neighbor from your training data set. So what happened here is that, okay, I will accumulate all those values, all the label that we have for the k neighbor, and then I will assign the average to the new instance that we have. Okay. So it could be numerical value or it could be the mode value. Okay. So we are looking at the majority voting here. What are the majority classes that belong to the k nearest neighbor? And then we will assign that majority class to the new instance that we have. This is our new instance. Okay, new instance. So in the k nearest neighbor, the letter k here referring to any number of nearest neighbor could be used. So it could be 2, or it could be 3, 4, 5, and so on. And the critical aspect of this is that how do we choose the best k? What is the best k? Okay, what value of k that will give you or will maximize the accuracy of your data? So this one, for every set of data that you have, you need to run a test, because different data set will have different characteristic, different effect, and it will give you different accuracy. Okay. So for example, let's suppose we have this data here. So we have food type, we have fruit, protein, class, veggie, and so on. So this is your class label. Okay, so this is your class label, and then this is the item that you have, and this is referring to the sweetness and crunchiness. So if we plot them in a 2D graph, so we have all of them on this graph here. Okay, so if we group them based on the food type that we have, then we have a grouping here. Okay, so veggie, fruits, and protein. So let's suppose we have a new one, a new symbol here, a new tomato. So what is the label for this new tomato here? Will it belong to the fruits, veggie, or protein? Okay. So our task is to measure the distance between the new item, which is the tomato, to the other member in each of the class that we have. So it also depends on the k value that we have. Okay, so the idea is to assign a label to this tomato, which is vegetables or fruits or protein. And we will decide that one later on based on the majority label that we have when we apply k number of nearest neighbor. Okay. So the advantage and disadvantage of this nearest neighbor is that this is a very fast training, because we simply calculate the differences or we calculate the similarity. So we don't lose any information because we apply or we use all the feature that we have. And the disadvantage is that sometimes it will be very, very slow, because if you have million of rows, million of instant, then that means you need to do millions of calculation to find the most similar item that we have. Okay? We need lots of storage because we have millions of data. Okay? And it could be easily affected by noise. Noise means you have something which is not in line with the same class. So you have one guy who is away from everybody. So this is what we call outlier. Okay. So these are the advantages and disadvantages of the nearest neighbor, but most of them give you good performance. Okay. So how do we measure the distance between two samples? We can use the Euclidean distance or the Manhattan. So the formula here is defined by this vector. So we have two vector x1 and x2. Okay. So for each item in the vector, we will find the differences, and then we will take the n here. So this is for equivalent distance, n is equal to 2. So in this case, we take the square, and then we add up all the square differences, and then we take the square root. Okay. So for the Manhattan block, so n equal to 1. Okay. So we also use normalization because we do not want to have one column to have big impact on the differences. For example, salary and age. Salary has higher impact compared to age. Okay, if you want to find the differences between two rows in your data, so salary will give higher impact because they have bigger or large number compared to age. Okay, so we can use the standard deviation or range in order to normalize them. I'll show you later on. We could also use symbolic feature. Okay, so this is for numerical values. If you have all the values in numerical, but if you have symbol, so male you match with female, so this is 0, or male is equal to male, so this is 1. We could also use this value difference measure where we find the conditional probability differences between two values. So this is the first value, this is the second value. So we are looking at, given this value, what is the probability of having this value in this class, CH. Okay, so basically we are looking the differences between conditional probability of using different value. Okay, so in most cases we will use this numerical values. So we will use the equivalent distance. In our example also we will be using equivalent distance. Okay, so let's go to the example here. In the previous slide we are looking at the tomato. So how do we compute the distance between two items in our data set? Okay, so this is equivalent distance here, where we are looking at the differences of all the items in the vector, and we take the square, and then we add up all of them and take the square root. Okay. Okay, suppose we are looking at the tomato here. So the tomato has sweetness 6 and crunchiness 4. And the green bean has sweetness 3 and crunchiness 7. Okay, so the differences between the tomato and the green bean is that we are looking at this one. So 6 minus 3, 4 minus 7. So 4 minus 7. We take the square, add up all this together and take the square root, we get 4.2. So this number show you the differences between green bean and the tomato. Okay. So we can also measure the differences between tomato and grape, which is 2.2. And then tomato and nuts, and also the orange. Okay. So this tell you which one is the nearest neighbor, which is this one. Okay. So if we take k equal to 1, that means the most nearest neighbor. So we can take this food type, fruit, and we assign this one to the tomato because k equal to 1. Okay. But if we are saying k equal to 3, so that means we are looking at the 3 nearest neighbor. So we are looking at this, and these 3 ingredients. So we are looking at the label here. We look at the majority. So majority is fruits. So we will assign fruits as the label to the tomato here. So notice that k equal to 1 will give you fruits. K equal to 3 will also give you fruits. Okay. So you can do a lot of experiment to show which k is the best one, which k give you the highest accuracy. So this is how we how do we assign label to the tomato based on the nearest neighbor that we have. Okay, but choosing k is a very critical issue because if you choose larger k, when you choose larger k, that means you need to fulfill more requirement. So when you want to fulfill more requirement, that means your separator or your model will be a straight line. So when you have a straight line, that means you will cause underfitting. So underfitting is where your model perform poorly on the training data, but perform well on the evaluation data. Because when you have a straight line, the distance between the line to the all the sample that you have will be bigger. Okay, so when you do the actual testing, so your model actually give you higher accuracy, but during the training you will have lower accuracy. So when you have lower versus higher during training and testing, then this is what we call underfitting. Okay, but when your k is smaller, that means you would be able to go to individual point, so you will have something similar to this. So you may have higher accuracy during training, but when you do the testing, you get lower accuracy. Okay, so that is what we call overfitting. You perform well during the training, but during the evaluation, you have lower accuracy. Okay, so what we want to do is we want to have this just nice number of k that you can avoid the underfitting and overfitting of your model. Okay, so this is when you have larger k. So larger k means you have to go to straight line. So when you have to go to straight line, that means during the training you will have higher accuracy, when you do the testing, you have lower accuracy. Okay. Yeah. So no, when you have this one during the training, you will have poor. But when you do the testing, you have higher. But when you have smaller k, that means your training, you will have higher accuracy. But during the testing, you have lower accuracy. Okay. Okay, the problem is that we do not know whether the straight boundary or the soft boundary better represent the true underlying concept to be learned. Okay, so one common practice is to set k equal to the square root of the number of training. So if you have 100 sample, so the best k would be square root of this, you get 10. So your k is 10. Okay, so this one will be the best practice. So you start with 10, given 100 samples. So you can move k up or you can move k down. Okay. Okay, so like I mentioned just now, before we can perform the finding the similarity, we need to normalize them. So normalize is very important in order to remove the bias of differences between big range of data to small range of data, for example, salary and age. Okay, so for that we can use min max. So min max basically find the mean of that particular column and max, and then the range will be from 0 to 1 after you normalize them. So each of your column or features will only have values between 0 and 1. You could also use the z-score, which also look at the mean and also the standard deviation in order to normalize your data. So you could use min max, or you could use mean and standard deviation. Okay. Okay, for symbolic, so if they're male, then they say 1. Matching, if they are not the same, so that means it will be 0. So this is very straightforward. Okay, so when we perform the modeling, basically we didn't do anything. We just, when we trying to classify or to perform classification using can, and basically we skip all of this. We skip all of this. Okay, if you remember, if we use decision tree, we have to construct the tree. But in this case, if we use the can-and algorithm, we basically measure the distance only. So there are no modeling. So we skip this abstraction and generalization for the data that we have. And sometimes they call it lazy learning because we didn't do any abstraction. We just compute the differences, or we compute the similarity. Okay. And an instant-based learner do not build a model because we do not do any modeling. The method is said to be in a class of non-parametric learning. No parameter are learned about the data because we just simply do the finding the similarity of each item in the vector that we have. Okay. Okay. Because nearest neighbor depends on the number of feature that we have. It will have problem if we have more number of features because we need to find or compute the similarity based on the differences of all the feature that we have in our data. So our target is we want to find relevant features only that can be used to measure the differences between two items or two instance in our data set. Okay, so nearest neighbor is easily misled when you have high dimensional X, which means high number of features. Okay, so if you have low dimensional, then it's better. So what we want to look at here is how do we select relevant features? How do we reduce the number of features that we have? So in order to do the feature selection, we can use the info gain. Okay, and there are two approaches here. The first one is called filtering approach. The second one is called wrapper approach. Okay, so the filtering and the wrapper approach, how do we define this is depending on what method we use in our feature selection. Okay, let's take a look at the first one here. Okay, before we can perform any testing, so during the training here, we will select a subset of feature that we want to use in order to model them. So the optimization algorithm will be used in order to select the best subset of the features. So we will go around here in order to find what is the best number of subset feature that we have. And the function that we use to evaluate will be not the same as this. So they are not the same. Okay. So which means that we filter the features based on different method. And when we perform the testing, we use different algorithm again. So this is, we call it filtering because we are using different approach to filter them. But when we compare to the wrapper approach, you see this error, this two ways arrow. So that means during the feature selection, we use the same algorithm to evaluate our model here. So that means during the testing also we will do use the same algorithm. So since we are using the same algorithm, that means we are wrapping the whole process of training and testing in the same, using the same algorithm. So that's why they call it wrapper. If you compare with the previous one, this one is a different method and this one is a different method. So which means we are filtering the feature using different method during the training compared to the testing phase that we have. Okay, so that's the difference between feature selection using filtering and feature selection using wrapper. Okay. Okay, so we could also use feature weighting. So feature weighting is basically we put different weight on the feature that we have. Or so, for example, if we have data, okay, so we have, let's suppose we have 5 features. So we could put a feature like 1, 0, 1, 0, 1. That means you only include these 3. So this is basically feature selection, right? So we select only those that has weight 1. But we could also put weight something like this. So we could put 0.1, 0.1, 0.1, 0.1, and then 0.6. So we take this weightage and then we multiply with the content that we have in each of the feature that we have. So that means okay. Are you still there? Am I still connected? If you are still there, can you type number 1?
Yes, Prof.
Okay. Okay, so we continue. Okay, so we continue with this one. Okay, so this is feature weighting, which means that we are giving different priority to the feature that we have. Okay, so let's take a look at this diagnosis breast cancer. So for this one, we are utilizing the Wisconsin breast cancer diagnostic dataset. So we have 569 example that we have, and then we have 32 features. Okay, so the idea here is that we will read all the example that we have, and we have 32 features. Okay, so we have the ID. Okay, so this is the label that we have. So we have benign and malignant. Where is that? Not here yet. So this is the label that we will be using. Of course, the ID will not play important role here, so we will ignore that one later on. Okay. So for that reason, we will remove this one. So that means I will remove the first features, which is the ID here. Then I will update my database again, dataset. So now I only have 31 variables. Okay. And if we looking at the distribution, so we are looking at the label that we have here. So we have around 357 sample belong to B or benign, and 212 belong to malignant. So these are the two labels that we have. Okay. Okay, we also look at the label that we have here. Since this is the label that we have, so
Prof, you forgot to unmute.
okay. Let's start over from here, right? And as function that we have defined here, then we put all the value 1, 2, 3, 4, 5. So the maximum value is 1. So the maximum value is 1, minimum value is 0.0. So even if you have one column that has different range, you will only be having values between 0 and 1. So these two will give you an example that if you have different range for your features, it will be reduced to 0 and 1. So how do we apply the normalized function? So over here, we will apply all this normalized function to the column number 2 up to column number 3.
Prof, is there a slide? Because we don't see a slide.
Oh. Since when you didn't see the slide?
Just now after you forgot to unmute, they're stuck.
Okay. Okay. So that means I need to go back again. Huh? I think
Yeah.
from here, right?
The
Okay.
next, yeah.
Okay, so this is the data that we have. So we have 5, 6, 9 examples, 32 features. So when we import them here, when we import all the data that we have here, in this statement, basically we are looking, say that, okay, I will import all my data here from this CSV file, but over here, meaning that I will maintain all of the data to be characters, okay, to be characters. So that's why when we read this data, this is in double quote. Double quote means they are in characters, okay. So the next thing what I want to do is I want to remove this ID because this ID has nothing to do with the classification. So I will say -1 here, meaning that I will remove the first features and I will update my data here. So now I only have 31 variables. Okay. So if I look at the proportion of data that we have here, so we can use this table command and focus on only this column. So features diagnosis. So it gives us the number of sample for each of the B and M. At this point, our diagnosis is still in character. Okay. So if I want to change them into vector, so I can use this format here. So saying that I will change my diagnosis from B and M into benign and malignant. So this is our label. Okay. So now my label only have benign and malignant. Okay. So next one will be, this one is just looking at the proportion number of samples that we have. Okay, so we have 62% and 37% that we have here. Okay. So when we look at the value for all the feature that we have here, so all of them will give you different mean and different median, min and max. So in order to avoid the differences of all this different value of each of the column, so we need to normalize them. So we can normalize them using the min max. Okay, so all the min max here. This is the function called normalize. So I will take the difference between the item with the min divided by max minus min. So this is the formula that we looked at just now. So if we try to use this normalized function using this value that we have, the range of value will be 0 and 1. Okay, similar to this, it will give you the same range also. So that's what we want to do here. So what we want to do here is that we want to apply the normalized function here to all the features that we have in our data set, and I will apply them, and I will create a data frame and put them as normalized data here. So notice that when we are looking at one of the feature, our min and max is this one only. Okay. Okay, now of course, when we learn about this nearest neighbor, we do not have any modeling here. But for the sake of doing the experiment, we just say, okay, for row number 1 up to 469, we will use that one for training. And for the remaining rows, we will use them as to for the testing. Okay, so this one also, we are looking at the first column. The difference between this one is we are looking at all the column. Okay, this one we are looking at the first column. So we are keeping the label for the training and also for the testing. Okay, so this is the label. We keep the label here. Okay, how do we call this KNN? So we just say KNN, we give them the training data set, the test data set, the class, and also the K here. Okay, so we install and then we upload into the memory. Okay, so this is the KNN that we have. So this is the training data set. This is the testing data set. This is the class label. And this is the K that we have. Okay, so this is the prediction that we have. Okay, so we can perform two tasks here. So one is K equal to 21 and the other one is K equal to 10. So basically the only difference is K. Okay, so we store the result here. So one is test prediction and the other one is test prediction 2. Okay, so in order for us to display the accuracy, we have to plot the cross table. The cross table will give you the true positive and true negative table that we have. So we use the graphic model here. So this one will give you this table, and the second one will give you this table. So what we are looking here is that because this is the test label, this is the predicted label, this is the true positive and true negative. So they are okay. But what we want to do is we want to reduce this. We do not want to have this because they are errors. Okay. So for this one, the accuracy is, because we have 2, so that means the accuracy is only 98%. For this one, the accuracy is 96%. Okay. So different K will give you different accuracy. So you can have many runs, K equal to 15 and so on. So, or even you can plot a graph to show what are the effect of varying the K here. Okay. Okay. So that one will give you some idea how does the K nearest neighbor works. Okay, I'll be sharing the file here. The file that you need to run for this one will be this data set. I'll be sharing that one in the itel.ums. Okay, so the whole idea is we are looking at the can here. So we call the can here here. So we need the training and also the testing. The testing is used to find how many of them are correctly classified. The training is used to measure the distance, and the class is just to double check with, because these two will be used for your testing. So K here is a variable that you can change. Okay. Okay. Any question? Do you know when is your exam? When is your exam?